तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The last few lectures we have discussed the Fourier transform technique for the analysis of linear networks and systems. You recall that the Fourier transform technique is considered very appropriate in dealing with networks and systems which are characterized by their frequency response function, either because the frequency response function is deduced experimentally using convenient techniques, or because the specifications in terms of frequency response comes naturally for such systems or networks, for example filter networks. However, for the analysis of general linear networks, for the transient performance, that is, the Laplace transform offers a number of definite advantages, and for this particular application it is unrivaled, and therefore we would like to spend some time now in discussing the Laplace transformation techniques for the analysis of linear networks and systems. For the first few lectures we would like to discuss what is meant by Laplace transform and find the transforms of several important time functions and the properties of the Laplace transforms. Then we will take up the question of its application to various networks and systems. In the Laplace transformation, the type of Laplace transformation that we talk about is what is called unilateral Laplace transform. So this is the type of Laplace transformation that we are going to talk about. What we mean by that is, we assume that f of t is 0 for t less than 0. So our discussion will be limited to f of t which is 0 for t less than 0, that means causal time functions. If indeed we have an f of t which fails to be 0 for t less than 0, we simply disregard the value of the function for negative values of time. We take it to be 0 even if it was not originally 0. So our discussion will be confined to such functions, and this is not a great disadvantage, because in transient analysis of networks and systems some switching takes place at a particular point of time, and what follows that switching operation is what is important to us, and we can always take the switching to take place at t equals 0, and the past history of the circuit, the network or system, is summarized in terms of the energy storage in certain elements, for example in electrical network in the reactive elements. So the energy storage in the reactive elements at t equals 0 plus the knowledge of the excitation function from t equals 0 onwards for positive values of t, these two factors determine the response of the network uniquely for t greater than 0. Therefore, if you know the excitation function only for t greater than 0 and process that, that will not entail any loss of generality, because the whatever is needed about the past history of the network is summarized by the conditions in the reactive elements. So this does not lead to any loss of generality as far as transient performance is concerned. Now, the Fourier transforms of certain time functions is what we have already derived. However, you would notice that Fourier transform does not exist. Fourier transforms do not exist for certain time functions. For example, if f of t is e to the power of 2t ut, then the Fourier transform of such a function does not exist, because the defining integral for the Fourier transform is, which is e to the power of 2t e to the power of minus j omega t dt. When you integrate from 0 to infinity, that integral does not converge. Therefore, this does not exist. So, the Laplace transformation, what it does is enlarges the type of functions for which Fourier transform the type of functions which are handled by Fourier transform. That means, Laplace transform enlarges the type of functions for which we can find out the transforms. That means, certain functions which are not, for which Fourier transforms do not exist, lend themselves to Laplace transformation, and therefore it enlarges the class of networks, class of functions for which transforms can be found out. How do we do that? To do that, let us consider the Fourier transform of not f of t, but f of t multiplied by e to the power of minus sigma t. So, given an f of t, we do not find the Laplace, we do not find the Fourier transform of that as such. Let us consider f of t e to the power of minus sigma t, where sigma is chosen to ensure the existence of the Fourier transform of e to the power of minus sigma t f of t. So, even if f of t does not have a Fourier transform, if you multiply f of t by a suitable factor e to the power of minus sigma t, it is possible for us to have a Fourier transform. For example, if e to the power of minus 2t is multiplied by e to the power of minus 3t, then it becomes e to the power of minus t, then Fourier transform exists. So, let us see. So, the Fourier transform of e to the power of minus sigma t f of t by the definition is, I will consider Fourier transform of e to the power of minus sigma t f of t ut, because I mentioned we are assuming this f of t in our Laplace transformation technique to be those functions for which the value is 0 for t less than 0. To make it explicit, I am putting f of t u of t. Therefore, Fourier transform of f of t u t, this makes it very clear that this product will have 0 value for negative values of time. This is equal to f of t e to the power of minus sigma t e to the power of minus j omega t dt. And since we are talking about f of t ut, the integrand has 0 value for negative values of time. Therefore, this is 0 to infinity. Instead of minus infinity to plus infinity, I am taking to 0 to infinity, because f of t ut makes it 0 for negative values of time. So, f of t e to the power of minus sigma t e to the power of minus j omega t dt, and then this will be equal to 0 to infinity of f of t e to the power of minus sigma plus j omega t. Right. If the Fourier transform of f of t ut is f of j omega, then instead of minus j omega t, you have minus of sigma plus j omega t. Therefore, this will be a function f of sigma plus j omega instead of j omega, and this I will call f of s, where s is a complex variable having the dimensions of frequency and is given by sigma plus j omega. So, this f of s now, which is a Fourier transform of e to the power of minus sigma t f of t u t, is now expressed is also a Fourier transform, but instead of being a function of omega, we are treating this as a function of s. Now, the inverse Fourier transform, if you want to find out, inverse Fourier transform of this f of sigma plus j omega. How do we find this? The inverse Fourier transform of this must give us back the f of t e to the power of minus sigma t. So, f of t e to the power of minus sigma t, that is the inverse Fourier transform of this function. So, how do we find the inverse Fourier transform? Our usual formula, 1 over 2 pi minus infinity to plus infinity, that is, now this is an omega of course, because that is the defining inverse Fourier transform relation for the Fourier transform relation. If the integration is in terms of omega, this is f of sigma plus j omega e to the power of j omega t d. That is the inverse Fourier transformation of this f of sigma plus j omega, and if you apply the inverse Fourier transform, you must recover back your original function f of t e to the power of minus sigma t. Now, from this you can multiply both sides by e to the power of sigma t, then you get this 1 over 2 pi. Now, I am multiplying by this by e to the power of sigma t, and since e to the power of sigma t is independent of omega, which is the variable of integration, I can push it inside the integral sign without disturbing any value. So, I can write this f of sigma plus j omega e to the power of sigma plus j omega t d omega. Right. Now, that the range of integration now is an omega from minus infinity to plus infinity. But now, I would like to put this in terms of this new variable s we have taken. So, if s is equal to sigma plus j omega and omega is the one which is varying, then I can write this as, if omega is varying, then ds is equal to j d omega, because omega is the variable factor. How does s vary? When omega varies, ds is equal to j d omega. So, I would like to put the entire thing here in terms of s. So, if I do that, then what I would get is the integral now, when omega equals minus infinity, s will be sigma minus j infinity. When omega equals plus infinity, s will be sigma plus j infinity. So, it will be sigma minus j infinity to sigma plus j infinity, that is the variable of integration. F of sigma plus j omega is f of s, e to the power of sigma plus j omega t equals e to the power of st, and since d omega equals ds upon j, I write this as ds, and ds upon j, so I will write this 1 over 2 pi j. So, this means that we are having f of t as 1 over 2 pi j sigma minus j infinity to sigma plus j infinity of f of s e to the power of st ds. So, we have let us summarize what we have done so far. We are thinking of finding out the Fourier transform of f of t, but such functions of this type do not lend themselves to Fourier transformation. So, what we can do is we can try to decrease its growth by multiplying by a function like e to the power of minus sigma t, and choosing a suitable value of sigma, we can make sure that this function decreases with increasing value of t such that the Fourier transform integral converges. So, we are associating with f of t a convergence factor e to the power of minus sigma t, and this value of sigma is something which depends upon the particular f of t which you choose. Naturally, for each value of f of t there is a certain minimum value of sigma which we should have. We will see about that. So, after having borrowed this e to the power of sigma t minus sigma t as a convergence factor, we find the Fourier transform of e to the power of minus sigma t f of t ut, because we are going to talk about functions which are 0 for negative values of time. Therefore, the Fourier transform integration, instead of starting from minus infinity, can start from 0 itself, because the value of the integrand will be 0 for negative values of time. So, consequently, the Fourier transform of this will be f of sigma plus j omega, where instead of j omega we have sigma plus j omega, because that is now the variable which we would like to treat as the new variable. Yes. So, we have f of s therefore is f of t e to the power of minus sigma plus j omega t dt, which means f of t e to the power of minus st dt. After having find out this f of s, which is f of sigma plus j omega, if you would like to get back your original function of time, first of all we find the inverse Fourier transform, which is f of t e to the power of minus sigma t, and multiply that by e to the power of sigma t, which then you get f of t, which is goes like this, and finally you end up with this. So, instead of now always talking in terms of Fourier transforms by using this convergence factor, we may straight away talk in terms of a transformation with reference to the variable s. We can straight away say that given a function f of t, you have a transformation which is obtained by multiplying f of t by e to the power of minus st and integrating from 0 to infinity, that will give you f of s. And once you have got f of s, we can get f of t in this manner using this inverse transformation, and these two relations constitute the two central relations as far as Laplace transformation is concerned. So, the origin of Laplace transformation as an offshoot of the Fourier transformation is what we have discussed now, but let us here afterwards straight away define the Laplace transformation relations and then study the various properties. So, given any function f of t, we will indicate its Laplace transformation as f of s, where s is a complex frequency variable, which is a real part sigma and an imaginary part omega. And so, we indicate the function of time and Laplace transform pair in this manner. F of s is obtained from a given f of t by this defining integral 0 to infinity of f of t e to the power of minus st dt, and this is called the Laplace transform integral. The inverse Laplace transform is obtained from the Laplace transformation f of s by this relation 1 over 2 pi j f of s e to the power of st ds. Now, the limits of this integration I will explain in a moment. Now, for this integral to exist, as I said, there must be a convergence factor. E to the power of minus sigma t is a convergence factor which is built into the Laplace transformation. So, depending upon the type of function that we are considering f of t, there is a certain minimum value of the real part of s that we would like to have. So, the real part of s here for this integral to exist must be larger than a certain value sigma c, which depends upon the function f of t. Sigma c depends on f of t. And this sigma c is called abscissa of convergence. So, when deriving the Laplace transformations of various functions, we will just briefly have a look at the abscissa of convergence that is required. We assume the real part of s is greater than this. Fortunately, we do not have to keep track of the abscissa of convergence in the work related with Laplace transformations, because we always assume that the s value that we are using has a real part which exceeds the abscissa of convergence for the particular function or set of functions that we are dealing with. However, when you want to substitute a particular numerical value of s in certain cases, then you have to pay regard to the abscissa of convergence and make sure that the numerical value of s that you want to put into the expression satisfies that its minimum part is greater than sigma c. Normally, we do not have to bother about the axis of convergence in our routine work. Then, so in this transformation, that means if you take a this is your complex plane, S plane, sigma and omega. So there is a certain axis of convergence sigma c. That sigma c depends upon the particular function that we are dealing with, as I mentioned. And in this integration that we are having, the inverse Laplace transform integration, we are, you recall that when we derived this from the Fourier transform theory, we said c sigma minus j omega j infinity to sigma plus j infinity. So instead of that, I will simply put c minus j infinity. So c plus j infinity, where c is a value which is like this. So we do this integration from c minus j infinity to c plus j infinity, where c is the real part of S. So instead of sigma, I am using value of c just for convenience sake. So c minus j infinity to c plus j infinity is the contour of integration. So we are taking starting from c minus j infinity and integrating up to c plus j infinity in this direction. This is the what is called Bromwich contour. In literature, this is called the Bromwich contour, and so we are integrating this f of s e to the power of st along a vertical line in the complex frequency plane along the Bromwich contour c minus j infinity to c plus j infinity, where the value of c is greater than sigma c, the axis of convergence. So what we have therefore is the sigma c defines the region of convergence. This is the region of convergence of the Laplace transformation integral often abbreviated as ROC. So the Laplace transformation exists provided the value of S is in this region of convergence. That means the real part of S must be larger than sigma c, which is the axis of convergence, right. So real part of S, which is given by sigma, must be greater than sigma c. As far as the integration in the inverse Laplace transformation is concerned, we take a vertical line in the region of convergence. That means the real part of S could be any general value of c, but that c should be larger than the axis of convergence sigma c. So this is these two are the fundamental relations relating to Laplace transformation. We can also abbreviate this as Laplace transform of f of t. We can write this as f of s, and we can write inverse Laplace transform of f of s is equal to f of t. This is the alternate way of writing the forward transformation and the transformation in the reverse direction. So this then is the general relation that we need to keep in mind, and therefore before we proceed further, let me make a few comments. One, we will first say that the real part of S should be the axis of convergence, and this must be kept note of whenever we want to substitute numeric values of S, as I mentioned earlier. Normally, we do not have to keep track of sigma c in our usual routine work. Secondly, if f of t has impulses at the origin, then when you integrate from 0 to infinity, the impulse is sitting right at the origin. So to take care of the impulses which are present in the origin, we need to integrate through the impulse. Therefore, we must start the integration from 0 minus. So the Laplace transformation integral is taken to start from 0 minus to take care of impulses at the origin if any in f of t. So, f of s we take it as starting from 0 minus t infinity of f of t e to the power of minus st dt. If f of t does not have any impulse at the origin, it does not matter whether you take it from 0 or 0 plus or 0 minus. But if f of t has impulses at the origin, and if you want to include those impulses in the origin in your transformation, you must perforce start the integration from 0 minus. So, normally when we define the Laplace transformation integration, we take it starting from 0 minus to infinity to take into account these impulses also. A third point which we would like to note is that in the complex frequency plane, this is the Bromwich contour, and we are taking the integration along this, and so as you move along this line, you are incrementing omega. So, you can say you can divide this entire contour into small intervals of width delta omega, and suppose you have the center point is omega I, then we can think of f of t as composed of elementary exponential signals of the form e to the power of sigma, suppose this is c, e to the power of c delta omega I t, e to the power of c omega I t, with a this is the exponential signal, but with a coefficient density given by f of s times delta omega over 2 pi, and we take the summation of all such signals. In other words, we take this as limit as delta omega tends to 0. Let me rewrite this more clearly. F of t can be thought of as the summation at delta omega goes to 0 of a number of elementary signals, exponential signals of the form e to the power of c plus j omega I t. This is an exponential signal sitting at this point in the complex frequency plane, and its coefficient is f of s delta omega by 2 pi, because this is the coefficient density. We can treat this as a coefficient density just as we are treating in the case of Fourier transform. Now, in the case of Laplace transform, the coefficient density is f of s, because the complex frequency signal is e to the power of st rather than e to the power of j omega I t, and the density is defined as so much coefficient per cycle per second. Therefore, delta omega by 2 pi is what we have taken, and if you take this limit, then this becomes an integral, and so instead of delta omega we are putting delta s. Therefore, this can be taken as 1 over 2 pi j integral f of s ds by 2 pi j, ds by j becomes d omega, and then e to the power of c plus j omega I t is the running variable s, therefore e to the power of st, and we take the limit from c minus j infinity to c plus j. So, this is the defining relation, inverse Fourier inverse Laplace transform relation. So, even here, just as in the case of Fourier transforms, we can think of f of t as composed of number of exponential signals of this value, where omega I runs from minus infinity to plus infinity along this Bromwich contour, and at each particular frequency, spot frequency, there is a certain coefficient density, and the coefficient density is given by f of s multiplied, coefficient density is f of s, and so the coefficient of this exponential signal, which is concentrated in this small elemental width, can be thought of as f of s times delta omega over 2 pi. This is the coefficient density multiplied by the width. This is the coefficient of this particular exponential signal, and we take the summation of all such elemental signals along this line, then this becomes this integral. So, just as Fourier transform, Fourier integral splits up an f of t as an infinite summation of exponential signals e to the power of j omega t type, the Laplace transform also can be thought of as splitting up an f of t as a number of elementary exponential signals of e to the power of type e to the power of st, where s is a variable along this Bromwich contour, and having a coefficient density equal to f of s, and therefore the particular coefficient of e to the power of st would be f of s ds over 2 pi j. That is what we are having. This is an interpretation which will be useful later when we talk about the system function h of s, just as we talked about the system function h of j omega when we are dealing with the Fourier transform theory. So, this is generally the what we need to know about the introduction to the concept of Laplace transformation, the defining Laplace transformation relation, and the inverse Laplace transformation relation. Now, we will take up the question of Laplace transforms of various important time signals f of t and find out the abscissa of convergence for each of these in a routine fashion. We will do that. We will take that up next after having introduced ourselves to the concept of Laplace transformation. To start with, let us note the conditions for the existence of Laplace transform. This condition is usually stated as f of t should be of exponential order. In other words, f of t cannot grow with for positive t more than an exponent of some value, or in other words, there exists some sigma real value such that limit as t goes to infinity of e to the power of minus sigma t f of t goes to 0. So, there must be some real value sigma such that as t goes to infinity, e to the power of minus sigma t pulls down the value of f of t to 0 to negligible proportions as t goes to infinity. For example, if f of t is e to the power of 2t, e to the power of minus 3t makes it go down to 0. So, depending on f of t, you can choose the value of sigma, and the sigma should be larger than the abscissa of convergence as we have seen, or we can put this as limit as t tends to infinity of e to the power of minus sigma st f of t goes to 0 for some for real value of sigma, real value of s greater than some value sigma. So, that is what we are having. This is the abscissa of convergence. So, e to the power of minus st times f of t, as you push t to infinity, must go down to 0. It becomes negligibly small. So, the value of real part of s, which must be satisfy this condition sigma c, which is the abscissa of convergence, which depends upon the particular function f of t that we have on hand. So, this is, in other words, to put this in a very compact fashion, we say f of t should be of an exponential order. Now, we will take up Laplace transformation of important time functions. Important functions of time. Let us to start with, let f of t be delta t, an impulse at the origin. So, f of s equals minus 0 minus to infinity of f of t e to the power of minus st dt. This is the defining integral for the Laplace transformation. And in our particular case, 0 minus to infinity f of t is delta t e to the power of minus st dt. And what do we have? Any delta t e to the power of minus st dt, the characteristic of delta t e to the power of minus st, that means this is equivalent to delta t times the value of this function evaluated at s equals 0, that is 1. Therefore, in other words, we are integrating delta t dt over the interval 0 minus to infinity, which includes t equals 0. Therefore, the value of this is equal to 1. So, we have delta t has the Laplace transformation equal to 1, just like in the case of Fourier transform also delta t is equal to 1. This is also the same case here, f of s is equal to 1. So, I will write here a list of f of t and the corresponding f of s and the corresponding abscess of convergence sigma c. So, as and when we derive the Laplace transformations, we enter them here. So, delta t, the Laplace transform is f of s. As far as the abscess of convergence is concerned, it does not matter what value of s, what is the abscess of what is the real part of s, it will always be 1. It does not depend upon this. So, we may as well put this as nothing. We do not have any special particular restriction on the real value of s. Okay. Now, let us take f of t as ut, unit step function. Then we find the Laplace transform f of s as 0 minus to infinity, and in this range of integration u of t happens to be equal to 1. Therefore, I can write u of t e to the power of minus st dt, and since u of t is equal to 1, I may as well drop that and write e to the power of minus st dt, because u of t in this range of integration is equal to 1. Therefore, this will be e to the power of minus st divided by minus s 0 to infinity. And now, at the upper limit is e to the power of minus infinity times t, minus s times infinity. So, if real value of s is greater than 0, then you have say minus a small real value of s times t. Therefore, this will be e to the power of minus sigma plus j omega t, where sigma is the real part of s. So, as long as sigma is positive, real part of s is greater than 0, as that means as long as sigma is positive, when t goes to infinity, the magnitude of this, which is governed by e to the power of minus sigma t. After all, this is equal to e to the power of minus sigma t times e to the power of minus j omega t. The magnitude of this is 1 irrespective of the value of t, but the magnitude of this depends upon sigma and t. As long as sigma is positive and t goes to infinity, this goes to 0. Therefore, at the upper limit, we make sure that this goes to 0 by taking the real part of s to be greater than 0. Therefore, that is what we assume, and so at the upper limit this is 0, at the lower limit when t equals 0, this is equal to 1. Therefore, this becomes 1 over s, and therefore, f of s, the Laplace transform of f of t, which is ut, will be 1 over s, provided we take the real part of s to be greater than 0, and that means the integral will converge only if you take that particular condition, and that means the abscess of convergence for this sigma c happens to be 0, which is the real part of s, minimum value of real part of s that we should have. So, we have the relation now that u of t, the Laplace transform of u of t is 1 over s, and this Laplace transformation is valid as long as the real part of s is greater than 0 as positive. That means sigma c is 0, that means the real part of s must be some positive value which is larger than 0, of course. So, these are the two important functions for which we have found out the Laplace transformation. Let us move on. Okay, now we will take a third function, e to the power of minus alpha t ut. Then we take the Laplace transformation. Now, e to the power of minus alpha t ut, of course, is 1 in this range of integration, e to the power of minus st dt, which is equal to 0 minus to infinity e to the power of alpha plus s times t dt, which is equal to e to the power of minus s plus alpha times t divided by minus of s plus alpha evaluated between the limits 0 minus t infinity. Now, once again we would like to make the integral converge at t equals infinity by making sure that the real part of s plus alpha is positive number. Real part of s plus alpha must be greater than 0. So, when you make that, if real part of s is greater than minus alpha, if the real part of s is greater than minus alpha, at the upper limit real part of s plus alpha is greater than 0. Therefore, at t goes to infinity, this integral becomes 0. This the limit of this at t equals infinity will become 0. At the lower limit 0, this will be of course equal to 1. Therefore, it will be, and this is a minus sign already here. Therefore, this will be 1 over s plus alpha. So we have, yes, for a function e to the power of minus alpha t ut, the Laplace transform is 1 over s plus alpha, and this integral will converge provided the real part of s is greater than minus alpha. We are taking alpha to be real in this case. If alpha is real, this is what we have. Now, as far as this integration is concerned, it does not matter even if you are taken e to the power of minus zt, z is complex, then we go to the same argument, same analysis. It will be 1 over s plus z provided the real part of s is greater than minus of the real part of z. The real part of s plus z is greater than 0. So, even if this is zt ut of course. So, alpha need not be real, it could be even a complex number. Even if z is complex, the same relationship will be valid. So, I will write here e to the power of minus alpha t, alpha real 1 over s plus alpha, this is minus alpha, minus zt, z complex 1 over s plus z minus real part of z. So, once we have this relation, then we can find out the Laplace transformation of trigonometric functions. Suppose I take cos omega naught t ut. This can be written as 1/2 of e to the power of j omega naught t ut plus e to the power of minus j omega naught t ut. And since we have found out that e to the power of zt minus zt will have 1 over s plus z as its Laplace transformation, then we have, instead of z we have j omega naught. Therefore, the Laplace transformation of that would be 1/2 of 1 over s minus j omega naught, because e to the power of minus zt had the Laplace transformation 1 over s plus z. Instead of minus z you have j omega naught. Therefore, you have s minus j omega naught, and the Laplace transformation of this would be 1 over s plus j omega naught. So, if you complete this, this will become s over, when you rationalize, denominator will become s squared plus omega naught squared, s squared plus omega naught squared, and the numerator will be 2s, and divide by 2, this becomes s squared omega naught, s by s squared plus omega naught squared. In a similar fashion, if you find out the Laplace transformation of sin omega naught t ut as 1 over 2j e to the power of j omega naught t ut minus e to the power of minus j omega naught t ut, that is, after all, the sine function can be described in this fashion. This can be written as 1 over 2j 1 over s minus j omega naught minus 1 over s plus j omega naught, exactly in the same fashion. And in the numerator you get 2 j omega naught by rationalizing the denominator, and this 2 j will cancel with this, so you get omega naught over s squared. So that is what we are having. And in this derivation, the abscissa of convergence should be the real part of z. This is the running with z. The real part of this is 0. That means the abscissa of convergence for both these is 0. So we have the final result cos omega naught t. I can write this as omega t, because as long as you do not confuse this omega with the real imaginary part of s, we can as well write cos omega t, or if you like we can still continue cos omega naught t, then we can write this as s over s squared plus omega naught squared and sin omega naught t. This is of course always this ut continues with us, because we are assuming this function to be 0 for negative values of time. This will be omega naught over s squared plus omega naught squared, and the abscissa of convergence for this is 0. So that is what we are having for the sine function and the cosine function, which are truncated at t equals 0. That means the sine and cosine exist for only for positive values of time. Now we can represent the poles and zeros of these f of s in the complex frequency plane. For example, for these are all rational functions of time, therefore they exist, the poles and zeros exist for this. As far as delta t is concerned, it has neither poles or zeros. As far as u of t is concerned, there is a pole at the origin. As far as e to the power of the Laplace transform e to the power of minus alpha is concerned, 1 over s plus alpha, therefore there is a pole at minus alpha. Forget about this z. Taking these, you have for the cos omega naught t and sin omega naught t, there are 2 poles at plus omega naught and minus omega naught. The zeros will depend upon the cosine function or the sine function, as case may be. And now you observe that the abscissa of convergence in all these cases, this is 0. The abscissa of convergence is 0. Therefore, the region of convergence is the region to the left of the rightmost pole. In all these cases, you will observe that the region of convergence, which is defined by the abscissa of convergence, is the region of convergence is to the right of the rightmost pole. In this case is the rightmost. There are only 2 poles. That means entire region to the right of these poles is the region of convergence. The entire region to the right of this is the region of convergence. The entire region to the right of this is the region of convergence. That means the region of convergence is defined by the extreme pole, the rightmost pole that you are having for the particular function. More about this we will take up in the next lecture. To summarize what we have done today is, we said that Fourier transforms of certain time functions which grow exponentially do not exist, and to take care of such situations we can think of introducing a convergence factor e to the power of minus sigma t. So instead of finding out the Fourier transform of f of t, we can think of the Fourier transform of f of t e to the power of minus sigma t, and then try to find out the inverse Fourier transform and reintroduce, cancel out this e to the power of minus sigma t which we introduced in the first place. So both these formulas which we have lend themselves to the Laplace transformation formula. Becomes we do not have to introduce e to the power of minus sigma t artificially if we introduce a new variable s, which is sigma plus j omega. So the Laplace transformation evolves from such considerations, and we have f of s which is given as f of t e to the power of minus st integrated from t from minus 0 to infinity, and inverse Laplace transform is 1 over 2 pi j c minus j infinity to c plus j infinity of f of s e to the power of st ds. And this integration is along a vertical line in the region of convergence. The region of convergence is defined by the half plane where the real part of s is greater than a particular value which is called the abscissa of convergence, and this abscissa of convergence depends upon the particular function that we have on hand. And we then took up the consideration of Laplace transformation of various important time functions. In particular, we found out the Laplace transformation of the impulse unit impulse function at the origin, which happens to be 1 itself, the Laplace transformation of this unit step function, which is 1 over s, a particularly simple relation, and e to the power of minus alpha t ut, the Laplace transformation of that is 1 over s plus alpha, and then cos omega naught t and sin omega naught t give reduced to simple Laplace transformations of this type, s over s squared plus omega naught squared and omega naught over s squared plus omega naught squared. We will continue this discussion in the next lecture by enlarging the class of functions for which we find the Laplace transformation, and also we will look at some of the important properties of the Laplace transformation as such.